Log on, tune in, find out. Another good idea from Cambridge.
And then there's Pramod Ashar, who's going to continue his series of talks on derived categories and perverse sheaves.
Okay, so thanks. Yesterday, the setup was something like this. We started with an abelian category, and then we defined the bounded derived category. Well, we talked about how the objects of the abelian category can be regarded as objects in the derived category just in the obvious way. You think of one of these as a chain complex concentrated in degree 0. In fact, you can make a slightly stronger statement. This is A is actually a full subcategory of the derived category, and of course it's abelian to begin with. And this statement has a bit of content. The content is that, well, morphisms in the derived category are something quite complicated that we had to spend some time thinking about. And the content of saying that A is a full abelian subcategory of its own derived category is that if M and N are objects of A, then the Hom between them in the abelian category is the same as the Hom between them in the derived category. So that's something that requires a little bit of thinking, not too much. But the main problem for today is to try to find other abelian subcategories inside the derived category. Well, the main example of this, so I guess one of the words in the title, perverse sheaves, are going to turn out to be an example of this. They're going to be a non-trivial abelian subcategory inside some derived category. Okay, so here's the definition. Well, maybe I'll write the definition over here, and then I'll keep it up for the rest of the talk. So for the definition, I'm going to let D be any triangulated category. It doesn't have to be a derived category. And then suppose you're given two full subcategories of it, which are going to be called D less than or equal to 0 and D greater than or equal to 0. And as we go on, we'll get some intuition for sort of what kinds of categories these are supposed to be. So these are two full subcategories. And I'm going to define some other categories in terms of these just by shifting. So D less than or equal to N is going to be the same as D less than or equal to 0 shifted by negative N. And then same for D greater than or equal to N. Okay. So I'll go ahead and write down the definition, and then we'll look at a couple of examples. So the pair, so the given pair of categories, D less than or equal to 0 and D greater than or equal to 0, is called a T structure. If the following three axioms hold. So the three axioms are like this. So the first is that there are no non-zero morphisms between an object of D less than or equal to 0 and an object of D greater than or equal to 1. Of course, well, if you shift a pair of objects in a triangulated category, then the morphisms don't change. So you could you could change the 0 and 1 to any integer and the integer just after it, and that would be an equivalent condition. Second is some containment properties. So D less than or equal to 0 should be contained in d less than or equal to 1. And then for the greater than categories, the containment goes the other way. So d greater than 0 should contain d greater than or equal to 1. And then the last axiom is maybe the most important. And it says that for any object x, there exists a distinguished triangle, A going to x, going to b. Yesterday, I was always writing the distinguished triangles as 4 terms with a shifted by 1 as the last term. But I think I'm going to leave those off today just to save some writing. But anyway, so there exists a distinguished triangle. And the condition on this is that A belongs to d less than or equal to 0, and B belongs to d greater than or equal to 1. OK, so that's the definition. So here's an example. I guess I'll call this example 0. This is the motivation for this definition is that well, every derived category comes with sort of an obvious T structure, and here's how that works. So let's take D to be the bounded derived category of an abelian category, and then let d less than or equal to 0. What we're going to do is interpret these superscript inequalities as telling you where you're allowed to have cohomology. So d less than or equal to 0 is going to be the set of is going to be the full subcategory of chain complexes which have cohomology only in non-positive degrees. So the cohomology has to vanish for all n greater than 0. And then the greater than or equal to 0 category is defined in exactly the same way, with the inequality going the other way. This consists of chain complexes where the cohomology vanishes in negative degrees. And then, one has to check these axioms. And, well, what's involved in that? So axiom 1 says, well, you have to compute some Hom groups. So you have to show that if you have a chain complex with no cohomology in positive degrees, and then another chain complex with no cohomology in negative degrees or in degree 0, then the Hom group vanishes. And yesterday, we talked about how to compute a Hom group like this. It's something by taking an injective resolution of the second variable. And well, why does that come out to be 0? That's because if you start with a chain complex that has cohomology only in degrees greater than or equal to 1, its injective resolution is going to have terms only in degrees greater than or equal to 1. Number 2 is, well, those containments are I guess, obvious. And number 3, well, number 3 is you have to produce a distinguished triangle. And in this setting, you can produce actually something a little bit more special. You can produce a short exact sequence of chain complexes by hand, basically. You can take a specific chain complex and cut it off so that its cohomology in one bit stops in degree 0, and then in the quotient starts in degree 1 and goes up from there. Okay. All right, and then the theorem, which is the reason for defining T structures, is that well, it's this. So let D be a triangulated category with a T structure d less than or equal to 0, d greater than or equal to 0. Then the full subcategory, which is the intersection of those two, is an abelian subcategory. Okay, and this thing is has a name. This is called the heart of the T structure. Sometimes it's called the core, and then, well, I guess in French it's called cœur. So my conjecture is that, well, cœur means heart, and core seems to be sort of a mistranslation. So anyway, this is the heart of the T structure. So, for example, 0, well, what's the heart of the T structure? It's going to be the full subcategory of chain complexes with cohomology exactly in degree 0. So that's just the original abelian category that we started with. So the heart is the original subcategory A. Okay. Maybe let's look at one slightly more complicated example, and then I'll say a little bit about the kinds of things that go into the proof of that theorem. So this is going to be, well, maybe this is going to be this is not very different from example 0 in some sense. So I'll call it 0 prime. So the setup here is going to be that X is a topological space with a topological stratification, and what that means is that I'm going to write X in a specified way as a disjoint union of some smooth manifolds, and those manifolds are the strata. And there are some technical conditions on sort of how the tangent spaces of the various strata interact with each other. And I don't want to bother with writing those down, but I'll tell you how these things typically come up. The typical example for us is going to be X is going to be a complex variety, and then the strata are going to be orbits of some group action. And in this kind of setting, these technical conditions always hold, so it's not necessary to worry about them. Oh yes, finitely many orbits. Yeah, so this is supposed to be finitely many. Okay. Okay, and then here's a definition. A sheaf F on X is said to be constructible if its restriction to each stratum is a local system. So this is for all strata S. Okay. So this is a definition for a single sheaf. And then here's the derived category version of that. So I'm going to write dbcx. So B is for bounded, like usual, and the letter C is for constructible. This is the full subcategory of the bounded derived category of sheaves on X, whose objects are complexes of sheaves such that the cohomology sheaves of that complex are constructible sheaves. So Hn of F needs to be constructible for all n. And I guess this is the first example of a triangulated category, which is not itself a derived category. So this is a full triangulated subcategory of dbx. And saying that this is triangulated, that has some content, just like saying that A is a full abelian subcategory of dBA has content. The content here is, of course, you can take any collection of objects and talk about the full subcategory made up of those objects. But to say this is triangulated means that, you need to be able to form distinguished triangles inside the smaller subcategory. So the content here is that if you take any morphism between two complexes of sheaves in the subcategory, so if this is a morphism in dbcx, then the cone on that morphism is also in the subcategory. Okay. Okay. And now, actually, so the next thing I want to do is define d less than or equal to 0 and d greater than or equal to 0. So I'll just add a prime here. And then, so I'm going to use exactly the same definition as we used before. So now we're working in dbcx, but the definition is just going to be exactly this. So d less than or equal to 0 is complexes of sheaves. I guess I should change C to a sheaf-looking letter. So F. So this consists of complexes of sheaves whose cohomology vanishes in positive degrees, and this other one consists of complexes of sheaves whose cohomology vanishes in negative degrees. So far, this example looks pretty similar to the last one, and then of course the heart of this T structure is the abelian category of constructible sheaves. The difference is that dbcx is not the derived category of the abelian category of constructible sheaves. This is actually one of the exercises on my webpage for today to show this in a specific example. And what this says is that, objects of dbcx are complexes of sheaves of vector spaces whose cohomology is constructible. Objects of this category would be complexes whose terms individually are constructible. So certainly any object in this category belongs to this category, but not the other way around. Not every, so to say that these are not equivalent is essentially to say that not every complex of sheaves with constructible cohomology is quasi-isomorphic to a chain complex whose actual terms are constructible. Okay. Okay. So anyway, so as I said, so this is, I guess, our first example of a triangulated category, which is not a derived category. Okay. So one question one can ask when you have a T structure is, well, so I told you this theorem that says that the heart is an abelian category. So in the heart of a T structure, well, you know, I made a point yesterday of emphasizing that in the derived category, words like kernel and surjective and all those things don't make sense. In the heart, they are supposed to make sense. So what do they mean? So what are words like kernel and surjective? Well, here's most of an answer. Here's something that I think of as a concise way to understand what's going on. Most of an answer is this. If A, B, C is a distinguished triangle in the triangulated category with all three terms in the heart, then that basically is a short exact sequence in the heart. I mean, what I'm doing kind of looks like I'm not changing the maps between A and B or between B and C, but I'm sticking a 0 on the beginning and the end, and then this turns out to be a short exact sequence. And well, what does that mean? The kind of thing that's going on here is that the map between A and B, well, to prove this kind of thing, we need to prove that it's injective in the categorical sense. So we need to prove, or you know, that we need to prove that the map from A to B is the sort of categorical kernel of the map from B to C. And to give you a sort of a flavor of the way the proofs of these kinds of things work, I'm going to prove something, or sketch a proof of something that's a lemma on the way to proving this kind of thing, and is also something that's important in its own right. And the lemma is this. The lemma is that the distinguished triangle in the third axiom in the definition of a T structure is functorial. And then, well, this is one step on the way to the proof of the theorem. So here's what I mean by that. More specifically, there are functors which are called truncation functors. So they're truncation functors. They're less than truncation functors and greater than ones. So I'm going to write down two specific ones, which are the two specific ones we need for that triangle. together with a canonical distinguished triangle, which takes the less than or equal to 0 truncation of x to the greater than or equal to 1 truncation of x. And so what this says, the axiom just says there exists a distinguished triangle. This lemma says that not only are the objects in the triangle unique, but in fact the whole triangle is determined up to canonical isomorphism. So here's sort of a start of the proof of this. So here's maybe a proof glimpse. So this is going to be the beginning of a proof that you can sort of complete to a full proof. So the first thing to do is to prove that the triangle is unique before we prove, or at least that the objects are unique before we prove that the morphisms are also canonical. So let's suppose we have two triangles that satisfy that axiom. So let's call them AXB and A prime X B prime. Okay, so and of course the middle object is the same. So here's what I'm going to do to these. I can, well, one of the axioms from yesterday for triangulated categories that you can always rotate a distinguished triangle. So I'm going to rotate the first one. Well, the axiom rotated in one direction, and I'm going to rotate in the opposite direction. I'm going to move backwards and put b shifted by -1 at the beginning. And now that's also a distinguished triangle. And then I'm going to apply the functor ham ham A prime to this distinguished triangle. Okay. Okay, so one of the facts from yesterday is that well, we talked about ham as being H0 applied to R ham, and you get a long exact sequence from that. So the long exact sequence here is well, there's some term going into ham A prime comma b shifted by -1. So well, maybe I'll go ahead and write down the later terms also. So next is going to be ham A prime A, and next is ham AX. And then the term after that, well, the term after that is the next term that would be in the distinguished triangle, which is ham A prime B. Okay, so what can we do with this? Well, we know a few things. We know that well, the axioms say that A and A prime are both supposed to be in D less than or equal to 0, and B is in D greater than or equal to 1. So this is in D less than or equal to 0, and this is in D greater than or equal to 1. And then the first axiom says that that ham group has to vanish. So this is 0 by axiom 1. What about this first term? Well, what we did was take b and shift it by -1. So -1 means that, well, b started out in d greater than or equal to 1 anyway, and then this definition says that when you shift by a negative number, you increase the number in the exponent. So this is actually in d greater than or equal to 2, which is, of course, contained in d greater than or equal to 1, according to axiom 2. And then a prime is still in d less than or equal to 0. So this first Ham group vanishes for the same reason. And that means that these two are isomorphic. Okay. So those Ham groups are isomorphic. And well, we have a canonical element in Ham A prime x, because we started with the distinguished triangle, which has a map from A prime to x. So that means that there is a unique map from A prime to A, such that, well, I'll just redraw that diagram down here. So A goes to X goes to B. What we found is a canonical map going this way that makes this commute. And then, well, you could just repeat the same argument with A and A prime reversed. And then that's the usual kind of argument that you can use to show that A and A prime are isomorphic. So A and A prime are isomorphic. And then, of course, you could do the same thing on the other side and show that B and B prime are isomorphic. And they're not just isomorphic, you get a canonical isomorphism. And then somehow you're not far from finishing the proof of the lemma. Okay. Okay, so anyway, so maybe now let's define another T structure. So this is going to be example 1. And the setting is going to be the same as 0 prime. So X is a topological space with a stratification. Oh, sorry. Before I do that, I want to mention a couple other things about truncation functors. So all the various truncation functors, tau less than or equal to n and tau greater than or equal to n, commute with each other. And then there's there's a specific pair of these which has special meaning, and that's the composition tau less than or equal to 0, tau greater than or equal to 0. So when you apply this composition, well, that I guess just by the way it's defined, it obviously takes values that are both in the less than or equal to 0 category and in the greater than or equal to 0 category. So it takes values in the heart of the T structure. And so this is a functor which goes from a triangulated category to an abelian category. And it has a special name. It's called, well, it's called cohomology, and maybe I'll call it T cohomology to distinguish it from ordinary cohomology. This is and another notation for it is something like TH0. The thing to be careful about with this is that when we have a triangulated category with more than one T structure on it, then they're each going to have their own cohomology functors. And then in examples 0 and 0 prime, T cohomology just was ordinary cohomology. But later on, we'll see examples where it's something other than ordinary cohomology. OK. All right, so here's example 1. So now again, X is a topological space with a fixed stratification. I'm going to add an extra assumption here. This is not really an essential assumption, but it's going to make some formulas easier, and it's going to hold in the examples later in the week. So the assumption is that all the strata are even dimensional. Okay. So of course, if you're talking about complex varieties and the strata themselves are complex subvarieties, those are always going to have even real dimensions. So this won't be a problem. And then we're going to work in this triangulated category of constructible sheaves, and then I'm going to define a T structure with a left superscript P. So the P stands for perverse. And here's the definition of the less than or equal to 0 category. So it's complexes of sheaves where the dimension of the support of the nth cohomology is less than or equal to minus 2n. And I'm going to write down another equivalent formulation of this. We're working in the constructible category. So by definition, that means that whenever you take a cohomology of a complex of sheaves and restrict it to a single stratum, you have to get a local system. So a local system on a stratum, I guess maybe the strata should be connected for what I'm about to say to make sense. For a local system on a stratum, either its support is the whole stratum or it's 0. So what can you say about when this has to be 0? Well, this condition says the dimension of the support of this is at most negative 2n. So if you restrict it to a stratum whose dimension is bigger than this number, then this restriction has to be 0. So this equals 0 whenever n is bigger than minus 1/2 the dimension of S. So you should double check to make sure I got these inequalities right, or at least that they're equivalent to each other. But I think this is correct. And then the partner category that goes with it, the PD greater than or equal to 0. Well, it's possible to write down definitions of it that look more symmetric, but the easiest definition to write down is very far from looking symmetric. The definition of the greater than or equal to 0 category is that it consists of complexes whose Verdier dual is in the less than or equal to 0 category. And just to remind you what that is, Verdi dual is Rhom into some fixed object, which is called the dualizing complex. When I wrote it down yesterday, I wrote it down with just the constant sheaf here. So if X is an orientable manifold, omega X is just the constant sheaf shifted by the dimension of X. Okay. So then the theorem is that PD less than or equal to 0, PD greater than or equal to 0 is a T structure on DDCX, and then objects in the heart are perverse sheaves. That's the definition of perverse sheaves. So this is all a bit opaque. So this is some strange condition on dimension of supports and on Verdi duals. So I think in the time that's left, I want to try and say a little bit about what perverse sheaves actually look like, and what's good about them. So here's a theorem that tells us what a lot of the important ones look like. So let L be an irreducible local system on a stratum S. Okay. Then there exists a unique simple object in the category of perverse sheaves, and it's denoted ICSL, such that the following two conditions hold. ICSL restricted to S, well, is just the local system you started with, except it's not quite that local system because, well, there are these strange dimension conditions. So this is supposed to be in both the categories over there. So if it's going to be in the less than or equal to 0 category, the dimension of the support of any specific homology has to obey this inequality. And in order to get, you want the restriction to the stratum S to be non-trivial. You want it to actually be the local system you started with. So to obey that inequality, you have to shift this down by half the dimension of S. Okay. So here, of course, we're using the fact that all the strata have even dimension. And then the second condition is that the support of ICSL is the closure of that stratum. Okay, and then the end of this is that all simple objects in the category of perverse sheaves that arise this way. Okay. So the question is what is one of these IC objects? I mean, well, I guess I've been talking about a lot of abstract things about T structures and complexes of sheaves with some kind of support conditions. But these are specific objects in the derived category of constructible sheaves. And it would be nice to write down a description of one. And we're not exactly going to write down we're not going to write down a specific complex. We're going to write down sort of an approximate answer in some examples. And here's the kind of answer we're going to write down. So ICSL is an object of DBCX. So it's a complex of sheaves whose cohomology sheaves are all constructible. So that means that if you take ICSLX and you take a cohomology sheaf of it, and this is an example of sort of mixing two different T structures. This HN, this is ordinary cohomology of a chain complex. So this comes from the sort of obvious T structure on DBCX. But the object that we're taking cohomology of is an object in the heart of a non-obvious T structure. But anyway, the definition of constructible says that this object, when you restrict it to a stratum, is a local system. That's what the definition of constructible says. So maybe the best we could do is write down a table of all these local systems. So we're going to look at all the non-zero cohomologies of this, restricted to all the different strata, and just write down what local systems those are.
Different stratum. It's a different.
Oh, it's a different stratum. Yes, sorry. So let's write them all down. Okay, so here's example. I guess I'm on number 2. Example 2. So X now is going to be the following topological space. X is going to be the variety of 3 by 3 nilpotent matrices. And all of this is over the complex numbers. And I'm going to stratify by conjugacy classes. Or equivalently, orbits for the conjugation action of well, maybe I'll use SL3 instead of. You could do GL3 instead, but maybe I'll use SL3. So there are 3 strata here, which in principle, every undergraduate linear algebra student should know.
Oh, really?
What's that?
Really?
Well, maybe. So I'm going to call this strata, I'm going to label one of them with a P for the word principal. So this is the orbit of this matrix. And this orbit is dense in the whole thing. I'll record the dimensions of these also. And these are real dimensions. So if you're used to seeing half these numbers, don't get worried. Then the next one I'm going to call SM for middle. And this is the orbit of this matrix, and its dimension is 8. And then the last one is a singleton. It's just a single point, which is the 0 matrix. And its dimension is 0. And then I'm going to cheat slightly because up until now I haven't used the word equivariant anywhere, I'm gonna write down equivariant local systems, and this is the kind of thing where choosing SL3 or GL3 up on the previous board makes a difference. The equivariant local systems are, well, the bottom two orbits have only the trivial local system, so they have just the constant sheaf. That's their only local system. The principal orbit has well, its equivariant fundamental group is the cyclic group of order 3. So there are 3 local systems there. There's the trivial one, and there are 2 others, and I'll call them. I won't try to say which is which, but I'll just call the other ones L1 and L2. And then the closure relations are, well, they're really easy. They just form a line. So the closure of SP is everything. And then, so in particular, it contains SM, whose closure is itself and S0. And S0 is already closed. OK, so so now, if I want to carry out this project, so what I'm trying to do is describe IC objects approximately by taking their cohomologies and restricting to each stratum and writing down what I get. So there are going to be 5 IC objects in all, because there are 5 irreducible local systems among the 3 strata. And then here's what you get. So the answers are like this. So IC of on the principal orbit with the trivial local system, it turns out to be just a constant sheaf over the entire variety. So in other words, its restriction to each of the smaller strata is the constant local system on that stratum. Oh, sorry. These are all. So this has to be shifted down by half the dimension of this orbit. So this is shifted by 6. Okay. And then for the other 2 local systems on the principal orbit, ICSPL, well, restricted to the principal orbit itself, that theorem tells us that, I mean, this is just supposed to be the local system you start with. And both of these IC objects, there are 2 different ones here, they both have 0 restriction to the boundary. So ICSPL restricted to any other S prime is just 0. Okay. And then, let's see, IC. Well, I'll skip the middle orbit for now. I'll come back to that. ICS0 is, there's nothing to say there, basically, because there's nothing in the closure. I mean, there's nothing in the boundary, and its restriction to S0 is supposed to be just the trivial local system on S0. The shift here is 0, because we have to shift by half the dimension of that orbit, which is already 0. And then what's left is ICSMC. And this is the most complicated one. It turns out that this one, well, restricted to SM, it's, of course, the trivial local system shifted by 4. But restricted to S0, it's more complicated. Here's what it looks like. So remember that shifting by 4 means putting it in degree -4. So the -4 cohomology of this object restricted to S0 is the trivial local system That's in the same degree as the main part of it, the part supported on the middle orbit. But there's a tiny extra bit, and it's in degree -2. ICSM C restricted to S0 is also the constant sheaf. Oh, yeah, so that's also the constant sheaf on S0. OK, so maybe I'll spend 2 minutes writing all the information on that upper board again in a slightly different format. So what I want to do is encode the above calculations with polynomials. So there are 5 irreducible local systems among the 3 orbits, and there are 5 simple perverse sheaves, which have sort of the same names. And what I want to do is write down polynomials that tell me what local systems occur in what degree cohomology. So the first calculation up at the top says that when I take this IC object, I just have the constant sheaf in degree -6 on every stratum. So I'm going to write x to the -6 here, x to the -6, x to the -6. For these 2 local systems, well, this local system has L1 in degree -6 over SP, and it has zeros over the other 2 orbits. So I won't write down zeros. I'll just leave those blank. And this has an the L2 IC object has L2 in degree -6 and zeros on the smaller orbits. Then the second computation was that the IC on the 0-dimensional orbit is just the trivial local system in degree 0. So I'll put an x to the 0 right there. And then the complicated one was the IC object on the middle orbit, which has a trivial local system in degree -4 over the middle orbit. But on the 0 orbit, it has cohomology in 2 degrees. It has cohomology in degrees -4 and -2. So I'll encode that with that polynomial. OK, so we'll see more of these polynomials later on.
Are there any questions?
Yeah, go ahead.
By a simple object, what do you mean?
I mean, so the heart is an abelian category. So a simple object should be an object which has no subobjects other than itself and 0. So a subobject is just, I mean, so you have to define all these things in categorical terms. So what does a subobject mean in general? It just means an injective morphism from another object. So a simple object should be an object such that every injective morphism into it is either 0 or an isomorphism. Or you could define it dually and say that every surjective morphism out of it should be either an isomorphism or 0. So.
Okay, if there are no further questions, then we've got a break until 11:30. Thank Pramod again for some stuff.